in a car, which I don't recommend you do for reasons of energy, momentum, and forces hurting you when you go really fast and then go really slow all of a sudden. Okay, so don't race cars. But if you were on a horizontal sort of track, the thing that would be, if you were going around a curve, the thing that would be maintaining your circular motion would be the force of friction. That is, and what would determine the fastest that you could go around that curve would be determined by the Fs max. In problem 17, often you'll see in like racetracks that they'll bank the curve. So let's look at sort of like why that would allow you to go faster. So what we're going to do is we're going to assume that there's zero friction because this is our very own special racing track in physics land. But so here we know if this thing is going around in a circle, which way must the net force be? Inward. Okay, so this is sort of like your net centripetal force. Okay, so now let's see, what is it that's providing that force? Okay, well, let's check it out. All right, so you know that there's a normal force up like this. I would say that this, and I have drawn it horribly to scale. Maybe we can make that a little bit smaller. All right, that is your sort of net inward force, and I would say that it is equal to, if this is our normal force, that this normal force up here, that is the thing that is providing the centripetal force, is equal to Fn sine theta. And since that is the thing that is maintaining the circular motion, we could say that that is equal to mv squared over r. Okay, so now this question is asking us, what is the maximum speed that it could go... Oop, I erased part of the car. I hope that's okay. What's the maximum speed that this boxy car could go without sort of sliding? Okay, so we're saying, okay, Fn sine theta equals mv squared over r. So it's really only this component of the normal force that's providing that net inward force. Okay, so now the other thing, what else can we know? I'm going to say that like you may be tempted to sort of view this on sort of like a slanted axis, but let's not, because the force that we're looking at here is just a regular old horizontal force. But what we do know is that this is equal to mg, right? Because what would happen if they were unequal? It would either accelerate up or down. It's not doing any of the same, or any of the, you know what I mean, maybe? All right, so let's say this. I think that we can say that Fn cosine theta equals mg. I'm just sort of stating that that is the same thing. So now we have these two equations. All right, if you don't mind. Oh, you don't? Oh, that's so nice. Thank you. Let's substitute this in here, and we'll see some very nice stuff happen. So we got Fn sine theta equals Fn cosine theta v squared over g. And if we then isolate, whoop, for v squared, this is saying, okay, this is the speed when the thing providing the net inward force is that component of the normal force. So I believe you get, what, sine theta over cosine theta times g, and what happened to my r? Oops. Should be there, and it's the square root of this gigantic mess. Is that right? It is. Okay, so I get like, I don't know. What did I get? 23.7 meters per second. But that's the fastest you can go. Now, you could make it more difficult. What would happen if there were some friction? Well, there would be a friction that was opposing the sliding. That would be this way. You'd have to get the component, because a component of friction is also contributing to that net centripetal force. But let's not do that right now. Don't mind if we don't. Bye.